Welcome back to the deep dive. Today we're jumping into, well, a really fascinating corner of the number theory world, the OEIS, the Online Encyclopedia of Integer Sequences.
Ah, yes, a fantastic resource, like a giant catalog of number patterns.
Exactly, and we're zooming in on one sequence today, A000224. It's titled Number of Squares Mod N. Our goal is pretty straightforward. Figure out what the sequence is actually counting and, explore some of the interesting things about it. Sort of a quick intro for number theory students.
Sounds good. A000224 is definitely fundamental. It touches on modular arithmetic in a really core way.
And what's interesting is how just asking, how many different squares are there modulo n can lead some pretty deep places.
It really can. It connects outwards, quite surprisingly.
So, okay, let's dig in. This sequence term an, what's it counting?
Right. So an is simply the count of unique values you get.
Yeah.
Where you take the numbers from 0 up to n minus 1.
Okay.
Square every single one of them. And then find the remainder when you divide by n. So how many different remainders pop out? That count is an.
Ah, okay. So it's the size of the set of quadratic residues, modulo n plus 0, the numbers you can get by squaring.
Precisely. Those are the possible results of squaring. Mod n.
Now, the sequence starts 1, 2, 2, 3, 4, 4, 4, 3, 4, 6. I won't read the whole thing. It goes on for quite a bit.
Yeah. Yes, they often do.
But could we maybe walk through a small example? Just to make it concrete, like maybe N10.
Sure, N10's a good one. So we list the numbers 0 through 9.
0, 1, 2, up to 9.
Yep. Now square them. 0, 1, 4, 9, 16, 25, 36, 49, 64, 81.
Okay.
Now reduce each of those modulo 10. So find the remainder when dividing by 10.
Right. So 0, 1, 4, 9. 16 mod 10 is 6.
Yep.
25 mod 10 is 5. 36 mod 10 is 6 again. 49 is 9. 64 is 4. 81 is 1.
Exactly. So what unique numbers did we get? We got 0, 1, 4, 9, 6, and 5.
Okay, I see. 0, 1, 4, 5, 6, 9. 6 distinct numbers.
And there you have it. A10, 6, just like the sequence says.
Perfect. Now, something interesting from the OEIS page. It notes that for any n bigger than 2, an is actually less than n.
Yes. That's a really key observation.
What does that imply?
It simply means that, well, for any n2, you can't possibly hit every single remainder just by squaring numbers. There will always be some numbers between 0 and n1 that you can't get.
So there are always non-squares mod n, these quadratic non-residues.
Exactly. And the existence of those non-residues is, well, it's really important. It underpins things like certain types of cryptography.
How so?
Because finding square roots modulo a large number can be computationally very hard, especially if you don't know the factors of n. This difficulty is something that gets exploited.
Fascinating. Okay. The OEIS also says the sequence is multiplicative, and it gives formulas for A prime powers. How does that help?
Right. The multiplicative property is incredibly useful. It basically says if you have two numbers, say m and n, and they don't share any common factors besides 1.
They're coprime?
Coprime, yes.
Right.
Then am times n is just am times an.
Yeah. Ah, so you can break down the problem.
Exactly. You find the prime factorization of n, like n equals p1e1, p2e2, and so on.
Yeah.
Then you calculate a for each prime power piece, p, using these specific formulas.
And then just multiply those results together.
Precisely. It makes calculating an for large n much, much easier than squaring everything.
Okay, so what are these formulas? For powers of 2, for instance.
Well, for 2 to the power e, a2e, it actually depends if e is odd or even.
Oh.
Yeah. If e is odd, the formula is the floor of 2e6 plus 2.
Floor meaning round down to the nearest whole number.
Greatest integer less than or equal to, yes. And if e is even, it's a different formula, 2e1 plus 4 divided by 3.
Huh.
And the OEIS entry conveniently links to A023105, which just lists a to n directly.
Handy. And what about odd primes p?
For an odd prime p raised to the power e, so a, the formula is floor pe plus 1, 2p plus 2.
Okay, a bit more involved.
A little. But there's a really nice case when e is just 1. So just AP for an odd prime p.
Yeah.
It simplifies really nicely to just p plus 1, 2.
Oh, that's elegant. Why is that?
Well, think about it. You have 0 squared is 0. That's one value. Then for all the other numbers x from 1 to p1, x squared is the same as px squared modulo p.
Ah, right. They come in pairs that give the same square.
Exactly. So you basically get p1, 2 distinct non-zero squares plus the 0. Add them up, you get p plus 1, 2 total distinct squares.
Makes sense. And the OEIS lists specific sequences for powers of 3, 5, 7, 2.
Yeah, A039310, A039302, A039304. It shows how people track these specific cases too.
It's amazing how you can go from squaring numbers one by one to these quite sophisticated formulas based on prime factors.
It's the beauty of structure in number theory.
Now, there's a conjecture mentioned by Thomas Wadowski. It says n squared is congruent to 1 modulo an times an has 1 if and only if n is an odd prime. That sounds significant.
It is quite interesting, yeah. It's proposing this sort of unexpected relationship between the count of squares and whether n itself is prime.
A characterization of odd primes using an?
Potentially, yes, if it's true. The conjecture essentially says this specific calculation involving an works only for odd primes.
And it's been checked pretty far, up to 108.
According to Michelle Marcus's note on the page, yes. That's substantial computational evidence, which makes it, quite compelling. But it's still a conjecture, not a proven theorem.
It hints that there's maybe more structure related to an than we immediately see.
Definitely. Conjectures like this often point towards deeper connections.
The OEIS page also links to sequences about higher powers, like cubic residues, quartic residues, and so on. How does looking at those relate back to squares?
Well, it's about generalization, really.
Okay.
We ask, how many distinct cubes are there? Mod n is A000224. How many fourth powers? And so on.
Okay.
Studying these helps us see if the patterns and properties we find for squares, like multiplicativity perhaps, hold for higher powers too, or how they change. It gives a broader picture of the behavior of powers in modular arithmetic.
And there's another link, A005611, where an is just that sequence plus 1.
Right, an equals A10's fixie little n plus 1. It just shows these sequences are often related in simple ways. Sometimes one sequence is just counting something slightly differently, like perhaps A105612 counts only the non-zero squares. The OEIS is full of these kinds of cross-links.
It really paints a picture of this interconnected web of integer sequences.
It truly is a web.
And for people who want to play around with this themselves, there's code provided. Maple, Mathematica, Python.
Yes, and looking at the code is useful. You can see different ways to compute an. Some code might just do the direct definition square everything, count the unique remainders.
Which is slow for big N.
Right.
Right.
Others will use the multiplicative property and the prime power formulas, which is much faster. Seeing those different algorithms is instructive in itself.
You can actually run the code, test values, maybe even check the Wadowski conjecture for smaller n.
Exactly. Makes it hands-on.
So wrapping this up, A000224, the number of squares mod n. It seems simple, but it's not just a count. It connects to, well, the fundamental nature of modular arithmetic. It has this powerful multiplicative structure.
And it even leads to these deep conjectures about prime numbers.
Absolutely. It really demonstrates how much richness can be hidden in these seemingly basic number theoretic questions. For students, understanding an is a great stepping stone.
A foundation for more advanced topics.
For sure. Things like quadratic reciprocity, or as we mentioned, applications in cryptography. It all builds on these core ideas.
This was a great exploration, really insightful. I definitely encourage everyone listening to check out A000224 on the OEIS site. Click the links, maybe try the code.
And maybe think about this as you explore. We talked about squares modulo n. What about squares in other mathematical structures, like finite fields, or maybe rings of polynomials? Do similar counting questions make sense there? What properties might they have?
Extending the idea outwards. A perfect thought to leave our listeners with. Thanks for joining this deep dive.
My pleasure.